You're probably wondering, what the fire truck are Lagrange multipliers? Well, to that I say, slow down there, sport. You aren't quite ready to learn that yet. First, I'll introduce what they're for. An important problem in calculus is finding maximums and minimums, especially with constraint functions. Let's say we have a function f of x and y equals z, and we want to maximize z. Easy, right? Maybe, but now let's add a constraint. That is, g of x and y equals c, where c is a constant. We now want to maximize z such that only values that satisfy g of x and y equals c are included. You could try substitution, but with large amounts of variables, this could get really cumbersome. However, you shouldn't fear, because this is where Lagrange multipliers come in. Let's take a look at this graph. We have our function f, in this case a paraboloid, and our constraint g, an elliptical cylinder. What we wish to find are the extrema of the intersection of these two. How can we do this? Let's take a look at the level curves. As you can see from these different values of z, the extrema happen when the level curve of f is tangent to the constraint, since at that point the level curve is right on the edge of the constraint. Now, since the gradient is perpendicular to the level curves, and the level curve is tangent to the constraint, clearly the gradient of f must be parallel to the gradient of the constraint g. And since the gradients are vectors, that means that the gradient of f is proportional to the gradient of g, or equal to some constant lambda, times it. This constant lambda is what we call the Lagrange multiplier. For two vectors to be equal, their components must be equal. And as you recall, the gradient of a function has components that are just each individual partial derivative of that function. So that gives us a system of equations, the respective partial derivatives that make up the gradient, and then the constraint. Now we can just solve the system for x and y to find our extrema. Let's work through the example from the graphs. We had f equals x squared plus y squared, and g equals 2x squared plus y squared equals 2. For the gradient of f, we get the vector 2x, 2y, and 4x, 2y for the gradient of g. Thus, our system is as shown. If you think about it for a while, you'll come to the conclusion that lambda must be equal to 1/2 or 1, leading to values of 2 and 1 for z. So now we have both our maximum and our minimum values of z. However, note that the multiplier method does not tell us maximums or minimums guaranteed. Think about it like a first derivative test. It just tells us the critical points. This method can be easily extended to any number of input variables, even though we can't always visualize it well. In the example, the function f now has any number of variables you want to imagine being there. So even though you couldn't imagine it for any number greater than 3, it's still just the exact same method. Just find the gradient and the partial derivatives, and then solve the system you get when you combine these with your original constraint function g. As another example, let's consider the cliched yet familiar example of the topless box. What we want to do is maximize the volume v, where x, y, and z are our side lengths, such that the surface area, s, is say 5. Your function and constraint would look like this. It is left as an exercise for the listener to finish the process. Feel free to check your answer with older methods. Thank you very much for listening. You are now an expert in Chapter 14.8, Lagrange Multipliers.